All right, welcome back again. So yeah, still looking into waves today. Last time we talked about the wave, the speed of wave in the stream, so which is determined by the tension in the string and also the linear density. So we derived the equation using dimensional analysis. It turns out to be speed is equal to square root of the tension divided by the linear mass density of the string. And we also talk about the energy and power in waves. So it's proportional to the amplitude square, also the frequency square or angular frequency square, and then linear density, mass density. So the wave intensities defined by the energy over a certain area in the certain time t, where E divided by T is the power of the wave. So then intensity is equal to the power divided by the surface area. Okay. For a spherical wave that propagates three-dimensionally, so intensity for this point source then is P divided by 4 pi r square. Okay, so that's the spherical area at the distance r away from the source. Today we are going to look at the interference of waves. So let's say you have two waves, right? Or let's say you have a wave and it's interacting with a boundary condition, or maybe later on we'll see it will also when it meets another wave, so it will interact with another wave. So these are called the interference of waves. Okay, so for just one wave, if you have a string here, if one end is attached to a fixed point, so then the wave propagates here. When it hits this guy, it will bounce back. So this is called reflection of the wave. So when it reflects back, if this is a fixed boundary, then if the P comes in, will flip, okay? So then this is what happened after the reflection. Now, if you have free boundary, that means this end is free to move. So then the wave comes in, will reflect back like this. Will not have a flip of the wave, or this is called the phase, okay? So if you flip, then there's a phase change of 100 degrees or pi phase change. If this is free to move, then there's no phase change, okay? All right. Now, if the median density changes, so if you have thinner string here carries a wave and it hits the other thicker string here, so what happens is the part of the wave will transmit through into the second median, and then part of it will be reflected. So in this case, this is like a hard wall, kind of hard wall for the reflected wave. So this guy then will have phase shift. The transmitted one will not have a phase shift. Okay. On the other way around, if the wave goes from a dense median to a less dense median, then for the transmitted wave again has no phase change. For the reflective wave, there's no phase change either. Okay. So they are both having the initial phase. Now, when you have two waves in the same string, so let's say one propagate in one direction and the other one in the opposite direction, when the two meet, they will actually just add up. Okay, so this is called the superposition of the waves. So the amplitude will add up mathematically. So if you have A and A identical meet, then magnitude becomes twice 2A. After they meet, they behave like they never met, so they will just keep propagating with the original wave. Okay, so still A and A. Okay, so going in their original directions. All right. So when the two waves meet, if they add up, we call this as construct interference. Okay. So the two identical waves, they just when they meet, the peak and peak will add up. So then amplitude becomes twice of the original one in a sense. If the two waves, when they meet, if they cancel out completely, we call it destructive interference. So this happens when the two has a phase difference of 180 or pi in radians. Okay, so then here positive will meet minus, so we will cancel out, and then also here and here the same. All right. So let's take a look on the mathematics, more details of the mathematics of the two waves when they meet. Okay, so let's say they have the same amplitude A, and they have the same wavelength, so that the same wave number and then the same frequency, but they are different by a delta angle, which is small, okay? So when these two meet, then you basically have y1 plus y2. So that's the superposition, and mathematically you just add them up. So A will be the same, then you are just having sine of a specific angle here that will give you, and then plus sine of a different angle that is a little bit different from the initial one, okay? So you have A, that's called this as theta 1. So kx minus omega as theta 1, and then kx minus omega t plus delta as theta 2. So the trigonometry identity, one of them, right? If you do sine of theta 1 plus sine of theta 2, then you get twice of cosine of the difference of the two divided by 2, and sine of the sum of the two divided by 2, okay? So then for y1 plus y2, because a and a is the same, you can factor that out. So then it will be sine of this plus sine of that. So the difference of these two will give you delta, right? Divided by 2. Now you'll see that you'll get a minus delta, but cosine of minus delta is the same as cosine of positive delta. So then it doesn't matter. So you'll end up with twice of cosine delta over 2, and sine of, you have this one, so 2, right? Kx plus kx will be 2, but divided by 2, then you still have kx minus omega t plus, but delta divided by 2. So the result will be just y1 plus y2 equal to 2a, because there's a 2 there. Okay, so 2a cosine of delta divided by 2, okay, and then sine of kx minus omega t plus delta divided by 2, okay. Now, in the case of if the two wave functions are identical, that means delta equal to 0, okay. So then 0 here, cosine of 0 is 1, so 2a sine, so then it will add up of the original one, okay. So the two will add up, so wave 1, wave 2 will add up, okay. So if delta is equal to 180 or pi, so then cosine of pi over 2 is 90, right? Cosine of 90 is 0, or cosine of pi over 2 is 0, either way. So these two then are out of phase originally, so when they meet, they will cancel out each other. Okay, so this is then called destructive interference. Okay, let's take a look on this practice problem. It says two waves with the same frequency, wavelength, and amplitude. So just as the case we looked at before, right? They are traveling in the same direction if they differ in phase by 90. So that's delta is 90, and each has amplitude of 4. Okay, so in this case, it says what's the amplitude of the resultant wave, and then so then you have y1. If y1 is a, right, sine of kx minus omega t, then y2 will be a, the same amplitude, same wavelength, that means same wave numbers, minus omega t, then plus delta, okay? So it tells you if a is equal to 4, delta equal to 90, what will be then the new amplitude? So we know that for y1 plus y2, the result is 2a cosine of delta over 2. So this is the new amplitude, and times sine of, don't need that, minus omega t plus delta over 2. Okay, so this is a new amplitude prime. Let's call it prime. So it's asking you, what's this new amplitude then? So we have a and o and delta, then we just plug those two into here, right? So that is equal to 2a cosine of delta over 2. So 2 times 4 centimeter cosine of 90 degrees over 2. Okay, that gives you 5.66 centimeters. So that's the new amplitude. Okay. In part B is asking you for what phase difference will the resultant amplitude to be equal to 4. So this is asking you if my A prime is still 4 centimeter, then what will be delta? Okay, so then A prime, so this is still 4, so you set up 4 centimeter equal to twice of the original 4 times cosine of delta over 2, and solve for delta. Okay, so 4 and 4 cancels, so that means cosine of delta over 2 is equal to 1/2, right? Because 2 times 1/2 is equal to 1. So cosine, what angle is equal to half? 60, right? So delta over 2 is equal to 60 degrees. That means delta is equal to 120 degrees, right? Because 60 multiplied by 2 is 120. All right. So let's go back to the slide. So previously we have looked at when if you have two waves that have a different phase, right? So then that result in a difference, right? So it depends on what the delta, the phase difference is. So you could have constructed interference, destructive interference, or anything in between, right? So that's due to delta difference. Now let's take a look if everything else is the same, but X is different, right? So let's say you have two sources. So let's see if I can hide this guy. All right. So then everything else is the same. Let's say the phase is the same, delta is equal to 0. Omega is the same, amplitude is the same. So from source 1, you have wave generate and propagate to your point of interest. Now you have source 2, right? Generate and then at the point of interest there. So then the only difference is the path difference. So basically, so when you look at the arguments in the sine function, so if there's no initial phase difference, so you do this one minus that one. Okay, so the result is k delta x. Okay, so that gives you a difference there, and that's in terms of delta because it's similar, right? If you have no phase difference initially, but if you have the path difference, so then the result will be also giving you just similar to that guy, right? The same thing for here. If these two are different, if omegas are different by a little bit, then the result will be similar to just having a phase difference, right? Because the argument of the sign, the difference of there, okay? So if this is the case, then if this guy equals to 2 pi, right? Then it doesn't matter, right? So in this case, so when peak reaches here, for the second wave also peak reaches there, okay? So it might be just a difference of integer numbers of 2 pi's, okay? So then k times delta x, okay, is equal to just n times 2 pi, all right? So okay, let me see. Now, how do I get back my panel? All right. Just bear with me a little bit. Let me find my Zoom panel bar. I think I shouldn't have just hide it somewhere. Oh, okay. All right. Okay. So in this case, K times delta X is equal to 2 pi or any integer numbers of 2 pi. Okay. This guy, K is equal to 2 pi over lambda, right? Delta X equal to M 2 pi, right? So then delta X is equal to, you divide both sides or move this guy to the other side. So N times 2 pi over 2 pi divided by lambda. Okay, so then we can multiply by lambda. So 2 pi and 2 pi cancel. So the difference should be equal to just n times of pi, which n could be 0, 1, 2, 3, etc. Okay, so when that happens, then peak and peak will add up, or the value and the value will actually intensify in the negative direction. Okay, all right. So then that gives you the condition in the PowerPoint slide. If you are expecting constructed interference, then the path difference delta x should be integer multiples of lambda. And if you have distracted interference of the waves coming out from the two in phase, so that means they are, if one gives out the wave peak first, the other one will be also giving out peak. Okay, so that's in phase. And if it's out of phase, complete out of phase, that means one gives out peak, the other one then gives out minus peak. Okay, so in that sense. So distracted interference happens when the path difference is halves of lambdas. Okay, so that means when it reaches the point of interest, if you have peak here, then you have another one, another wave will have the value arrive at the point. So then those two will cancel out. So something like this. Okay, so peak arrives at point P, now value arrives there. With source 2, source 1 has peak there, source 2 has value there, so they will cancel out. Then you get distracted interference. Okay, now the other way around, if you have opposite phases, so then the condition flipped. Okay, so in that sense, it's a kind of like just have a phase shift initially, then of the pi. Okay, so then the two conditions completely flip. So in that case, if they're out of phase or in opposite phase, then you got distracted interference when the path difference are differed by more integer numbers of wavelengths. If you will then get constructed interference if the two path difference is half of lambdas. Okay. All right, let's take a look on this example. It says two speakers out of phase. Okay, so out of phase, then we have these two conditions, right? So either this one or that one. If you have the case of in phase, then you go to here. Okay, but out of phase, that means this page, conditions on this page. Okay, it says they are 3.5 meters apart, both pointing towards a wall, 5 meters in front of them. An observer standing against the wall midway, so in between. Here's distracted interference, right? Because they are out of phase originally. So for distracted interference, the two paths originally is the identical path or the same path. If let's say this is 6 meters, then this guy is also 6 meters. So I don't know exactly what number is, but just give you an example, okay? So he has to move to the side by 0.85 to hear the construct interference, okay? So in this case, then the path difference, x1 and x2, okay? That by, if you for construct interference, right, then it's by half lambda, okay? In that sense, so we should just write out x1 minus x2 then equal to half of lambda. Okay, so in that case, and let's do the sketch of this one as well. Two speakers, source 1, source 2. Okay, and then that's the wall. initially something in the middle, I have to move by 0.84 to here that. So then x minus 1, x1 minus x2, it is equal to half of the wavelength. Let's just connect it. So in here, this is midway between. So then this is 3.5 over 2 meters, right? And then this is also 3.5 over 2 meters. This is x1 and this is x2. Okay, so we can calculate x1 and x2, right? So this would be a right angle triangle. X1 will be equal to this square plus that square, right? And square root. Okay, so x1 is equal to square root of 3.5 over 2 meters, or actually plus 0.84 because that's the midway only, and squared, right? Plus this is the 5 meters to the wall. Okay, and then the other one, so x2 will be square root of 3.5 meters over 2 minus 0.84 meters. Okay, and squared plus 5.0 meters to be squared. Okay, so it looks like we can calculate this, and then the difference will be lambda over 2. So you can solve for lambda. Okay, so lambda over 2 equals to x1 minus x2. Then solve for lambda. Okay, it turns out to be 1.098 meters. Okay, now we are looking for the frequency. But it tells you the speed of the wave is 340 meters per second. So we know speed is equal to lambda times frequency, right? So we have lambda now. We can solve for the frequency. So V over lambda, 340 meters per second over 1.098 meters. Okay? So that gives you about 310 hertz. All right. Okay. Let's go back to the slide. So then we have looked at the difference due to the path and then difference due to the initial phase, right? So now let's take a look at the difference in the frequency, okay? So when there's a difference there, this is called the beats. So that's the interference in time. It's associated with time or frequency, okay? So if you have time difference, then it's equivalent to the result of having the two have a difference in their frequencies, okay? So in that sense, so then omega 1 and omega 2 are different, or T1 and T2 are different. So omega and T are related in that sense, okay? So let's call this as a Y1 and Y2. So that should be Y1, Y2 instead of gamma 1 and gamma 2. So the total Y will be equal to the two add up, okay? So we are just skipping the KX and then delta because those two are the same, okay? So then the difference will be here, and then the cosine, you can feed in the KX term and the delta term there. So if these two are close to each other, so then this guy is about 0. So then you get a new actually amplitude that is a cosine function. Okay, so these two waves add up, the result will be this guy. Okay, so amplitude changes periodically. Okay, so in that sense, so this is called the beat frequency. The difference of the two frequencies is called beat frequency, and then it's the absolute value of the difference. So it doesn't matter, okay, which one is greater, which one is smaller. All right, so the beat frequency is absolute value of f1 minus f2 then. Okay, so you can see the amplitude also oscillates as a sine or cosine function in that sense. All right, I think we'll stop here today then, and then we'll come back next time for the reminder of this chapter. All right. See you guys.